You are probably making a fatal shortcut in your Cambridge IGCSE Physics practicals right now, and it's quietly destroying your grade boundaries. Think ignoring a tiny unit or just rounding a decimal early doesn't matter? Think again. Examiners are aggressively hunting for this exact flaw. We are exposing this devastating trap today and fixing it instantly so you don't drop a single, precious method mark. Here is the harsh reality. It's the most common shortcut that lowers those grade boundaries. Students think, I'll just skip writing the units in my intermediate steps, or I'll round this number right now to save some time on the calculator. It seems like a totally harmless time saver, right? No way. It instantly crashes your mark scheme. Examiners call this premature rounding and unit dropping, and it literally drains points from your paper before they even look at your final answer. To put this into perspective, take a look at this, an aircraft flight deck. It's packed with analog and digital instruments. Now, just like a pilot relies on exact, unit-specific measurements from these dials to, avoid a complete disaster in the sky, your Cambridge examiner demands that exact same level of precision from you. You absolutely cannot afford to be vague when navigating physics. If you want those method marks, you have to treat your exam paper like it's a flight console.
So, why does ordinary revision fail so many students here? Well, they memorize formulas but totally ignore these fatal exam mistakes. Missing units, rounding too early, giving super vague explanations for practical improvements, using the wrong variables entirely, or making conclusions that literally aren't supported by their own data. These are the exact errors examiners see over and over when students measure length, time, or volume. It's just a constant bleed of easy points because students focus on the math and completely forget the scientific method.
Okay, let's fix this right now. To solve these errors and lock in your top band marks, you need a bulletproof, systematic approach. A quick win you can apply to literally any measurement question. It's our 4-part top band framework: concept, evidence and data, scientific reasoning, and finally, examiner wording. If you hit all 4 of these, you're not just writing an answer, you're essentially forcing the examiner to give you full credit. Let's break down exactly how to use it.
Right, so step 1 is the concept. In physics, the concept pretty much always starts with the 3 absolute basics we measure: length, mass, and time. But here's the catch. Before any measurement actually happens, you have to lock in a standard unit. We're talking about strictly utilizing the standard SI decimal metric system, where units are systematically divided or multiplied by 10. You have to explicitly show you know which SI unit applies to the concept you're testing.
But wait, the concept doesn't stop at simple scalar measurements. If your question involves vector quantities, think force or velocity, you have to actively account for differences in their direction, not just their magnitude. Like simple scalars that just have size. If you try to calculate a resultant vector and you forget to factor in the direction, bam, method mark's gone. So that's the concept. But here is where students start to panic. How do you handle the inevitable errors in single measurements? Let's be real. Any single measurement you take in a practical, whether it's the length of a wire or a really short time interval on a stopwatch, it's not going to be entirely accurate. It will always carry an error. And recognizing that is actually step 2. Evidence and data collection. You have to collect data knowing it's naturally flawed.
And that perfectly tees up step 3. How do we fix those inevitable errors? Well, the scientific reasoning you must clearly write down on your exam paper is that taking an average of several measurements or measuring multiples significantly reduces the size of the error. It's your ultimate defense against inaccurate data. You don't just say, I'll do it carefully. You say, I will take multiple readings and calculate the mean. That is the exact reasoning the examiner wants to see.
In a moment, I'll show you the examiner clue that changes the calculation completely. But first, you need this framework to understand why it's so vital. Because, think about it, what happens when your data spits out absolutely massive numbers, or microscopic ones? Say, the wavelength of light or the mass of a planet. How do you write that down safely without making a fatal transcription error? And that brings us to the big examiner clue, powers of 10 shorthand. This is the neat, examiner-approved way to write large and small numbers without dropping zeros. Look at this shorthand. 4,000 isn't just a 4 with some zeros. It officially becomes 4 times 10 to the power of 3. 0.04 becomes 4 times 10 to the power of -2. Using standard form like this isn't just a suggestion. For complex calculations, it's the only way to protect your answer. Which leads us directly into our final framework piece, step 4, examiner wording. A genuinely strong top-band answer must include the correct equation and substituted values using this exact powers of 10 shorthand. It's really not just about doing the math correctly in your head, it's about translating it onto the page. You have to speak the examiner's exact language to get the maximum points.
Check out this comparison. It brilliantly illustrates the difference. On the left, we have a deeply flawed student answer, just writing down 4,000. It completely lacks units and precision. The examiner looks at that and thinks, 4,000 what? Apples? Elephants? But on the right, the improved top band answer, 4 times 10 to the power of 3 meters. This secures full method marks immediately because it pairs the precise mathematical shorthand with the exact correct SI unit.
All right, now it's time for an interactive challenge. I want you to literally pause this explainer and predict exactly why this next student's practical investigation design is going to completely fail the mark scheme. Here's the scenario. A student needs to measure a very short time interval, maybe a pendulum swinging once. They measure it just a single time, and then they round their data early before doing their final calculation. What is the fatal error here? Take a guess. Got your answer? Well, they earn absolute 0 marks. Nada. Why? Because taking a single measurement of a highly variable, short event carries way too high of an error. By doing it once and then rounding early, their final conclusion becomes entirely unsupported by the data. It completely violates the core rule of reliable data collection we just talked about. So how do we jump in and fix this speedrun challenge like a Cambridge examiner? First, they should measure multiples, like timing 10 full swings of that pendulum instead of just 1. Second, calculate the average time for a single swing to drastically improve reliability. Third, retain those significant figures throughout the working, absolutely no early rounding. And finally, firmly state exact SI units, like seconds, at the very end. As the official exam guidance explicitly states, a strong answer should include correct terminology, substituted values with units where needed, and source page evidence. Fulfilling those command words means you are actively backing up your substituted values with correct physics terminology. You literally cannot just drop naked numbers onto the page and hope for the best. You have to undeniably prove you understand the physics behind them.
Which leads us to the ultimate practical check. Before you move on to the next page of your exam, run through this mental checklist. Are your precise units there? Are your significant figures consistent? Did you note any uncertainties? And honestly, the most important one, is your final answer logically reasonable? If you calculated the mass of a toy car to be 10,000 kilograms, you need to catch that before the examiner does. Now, you might be wondering, what if you apply this 4-step framework perfectly? You nail the units, you average your data, and you still lose marks on your data analysis section. Well, we've successfully solved the basic measurement trap here, but there is a totally new, devastating mistake waiting for you. It's all about graph axes errors and gradients, and it traps ordinary students every single time.
To ensure you don't drop those incredibly high-value practical marks, you need to understand the safe shortcut for Cambridge graph analysis, because plotting scale errors or messing up an anomalous gradient will entirely undermine all that perfect measurement data we just worked on. You need the safe shortcut to navigate those graphs without losing a single point.
Which means watching the next explainer isn't an option. It is your mandatory next step to secure that top grade. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click the next explainer on your screen right now to master the exact graph scaling and gradient safe shortcuts you need to survive. Don't let a simple graph destroy your perfect score. Click now and I'll see you there.